Well, let's continue our discussion. In the previous lecture, we talked about the Fermi function. The reason we need to understand the Fermi function is because it is used to compute carrier densities in semiconductors. When we do that computation, we'll encounter an integral known as the Fermi-Dirac integral. And that integral is what I would like to discuss in this lecture. Just a reminder, the Fermi function gives us the probability that a state is occupied in equilibrium, if that state exists. It's given by this simple expression. The two key parameters in this expression are the Fermi level E sub f and the temperature T. Okay. So our goal is to understand what the carrier density is in the conduction band and what the hole density is in the valence band, given a particular location of this Fermi energy. Okay. We argued that in the non-degenerate approximation that the probability that a state at the bottom of the conduction band is occupied is e to the EF minus EC over KT, so we expect n to be proportional to that. We argued that the probability that a state near the top of the valence band is empty is e to the EV minus EF over KT, so the hole concentration should be proportional to that. This applies to a non-degenerate semiconductor. But what is the constant of proportionality? And what if the semiconductor is not non-degenerate? Then what do we do? That's the subject of today's lecture. Well, there are two options in doing this calculation. Our goal is to relate the carrier density to the Fermi energy and to the other properties of the semiconductor. And we can do the calculation in K-space, or we can do it in energy space. I'll explain how we do it in K-space, but I won't actually do it. And then we'll discuss how to do it in energy space using the density of states. So consider again a chunk of semiconductor, a cube, carved out of an infinite slab of a three-dimensional volume of a semiconductor. This slab that we're doing the calculation in has a volume omega, length in the x direction, y direction times the length in the z direction. Now, if I wanted to calculate the number of electrons in this volume, we saw earlier that when we applied periodic boundary conditions, we had a finite number of k-states that were very closely spaced. I would just add up the probability that each one of those states is occupied in equilibrium. That would give me the total number of electrons in this volume. Now, the volume itself is arbitrary, so I'm really more interested in what is the carrier density per unit volume. So I would divide by volume. Okay. Now, if I were doing this calculation, I would realize that these states in any kind of significant size volume are very finely spaced. So I could convert this sum to an integral as long as I have the correct number of states in each element of K-space. The correct number will be given by the density of states in K-space. And remember, we computed the density of states in K-space. It was 2 for spin times volume over 8 pi cubed. So we can put this all together, convert the sum to an integral, perform the integral, and get the answer that we're after. Okay. All right, I'm not going to do that calculation. It's one that you might attempt and see if you can get the answers we're going to get in a minute here through the energy space argument. But it's a calculation that proceeds straightforwardly using the density of states in K-space and using this prescription for converting the sum over these finely spaced states in this volume omega into an integral, but accounting for the fact that we have the proper number of states there. We have to be careful when doing this that we include the valley degeneracy also. Remember, silicon had 6 equivalent valleys along the 6 directions, x plus x minus x, plus y minus y, plus z minus z. All right, what I would like to do now is to do the calculation in energy space and to actually work through it. To do the calculation in energy space, we're going to need the density of states. We've seen how it behaves in 1D, we've seen how it behaves in 2D, we've seen how it behaves in 3D. Let's do the calculation in 3D, where the density of states goes to 0 at the bottom of the conduction band, and then increases as the square root of energy as we go above the bottom of the conduction band. So first of all, let's take a look at some energy in the conduction band and ask ourselves, how many electrons are there in this shaded energy range here? Well, the number of states in that region is the density of states at that energy times the width of that shaded region in energy dE. Okay. Now, if I want to know how many electrons there are in that region, I take the number of states in that region and I multiply them by the probability that those states are occupied. That's given by the Fermi function. Here's my Fermi function. I can make my non-degenerate approximation because these states are way above the Fermi energy. And I'll remember that the density of states goes as the square root of energy. And then we conclude that the number of states in that region is proportional to the square root of energy times this exponential factor. Okay. So if I go ahead and plot that function, I'll get an expression that looks like this, that tells me where the electrons are located in the conduction band. As I increase the energy, the square root starts to increase and the number goes up. But as I continue to increase the energy, the exponential gets large and damps everything out and it turns around. So there is a peak in this. Most of the electrons are located, the highest probability of finding an electron is right there at that location. How do we find that location? Well, we differentiate this quantity with respect to energy and set it equal to 0. If you do that, you'll be able to show that this peak occurs at an energy that is 1/2 kT above the bottom of the conduction band. That's a relatively small energy. kT at room temperature is 0.026 electron volts. So that peak occurs at 0.013 electron volts above the bottom of the conduction band. The conduction band is 1.11 electron volts wide. So this is, I have mentioned from time to time that most of the electrons in the conduction band are near the bottom of the conduction band. This calculation shows that they actually are quite close to the bottom of the conduction band. Similarly, the holes are located within about 1/2 kT from the top of the valence band. So, electrons and holes are located very near the band edges. So now let's go ahead and do the calculation. Let's compute the electron density by integrating the number of electrons in an energy range over the entire conduction band. I'm going to integrate from 0 to infinity. Now I have a problem here you might worry about. My density of states, the square root of energy, only describes the density of states near the bottom of the conduction band. So it's not going to be a good approximation as I go to very high energies. But the Fermi function is going to help me out there. There will be virtually 0 probability that those states are occupied, so it doesn't matter that I'm making an error in the density of states. So if I put in the number of states times the probability that the states are occupied, integrate from the bottom of the conduction band to infinity, I know what my Fermi function is, I know what my density of states is. It's simply a matter of doing some math. I can see that the result is going to depend on Fermi level and temperature because those two parameters are in the Fermi function. The result is also going to depend on the effective mass of the semiconductor and the number of equivalent valleys because those quantities are in the density of states. Okay, so let's do the math. We have this expression to evaluate. We know the Fermi function and the density of states. If we plug those quantities in, we get an integral that we have to evaluate. Now, let me make a couple of definitions. I'll define a normalized Fermi level with respect to the bottom of the conduction band. Fermi level minus bottom of the conduction band in units of kT. That's what eta F is. And I'll define a normalized energy. Energy minus the bottom of the conduction band in units of kT. If I define those two normalized energies, I can rewrite the integral this way. And now it's simply a matter of evaluating that integral, and then I have my answer. All right, there's only one problem. That integral cannot be done analytically. It has to be done numerically with Simpson's rule or whatever. But we'll give that integral a name. That integral is called a Fermi-Dirac integral of order 1/2. Okay. The constants that we have out front here, we all wrap them all together, and those constants depend on the effective mass, and the temperature, just as I expected that they would. So that particular constant, n sub c, is called the effective density of states. It results from integrating the density of states over this energy range. So we have the expression that we're after. And let's talk a little bit more about this Fermi-Dirac integral, because I glossed over that pretty quickly. In general, we can define a Fermi-Dirac integral of order j this way. It's an integral of eta to the jth power d eta over 1 plus e to the eta minus eta f. And there's a normalization factor out front which involves a gamma function. Remember that this gamma function behaves like a factorial. The gamma function of an integer n is n minus 1 factorial. But the gamma function can also have, non-integer values. Gamma of 1/2 is the square root of pi. And there's a recursion relation that if I know gamma at some argument p, and I need gamma at an argument p plus 1, I can use this recursion relation to do that. The integral that we have encountered when we worked out the carrier density had a value of j equals 1/2, but it's simply an example of a more general function. Now, this integral has a very nice property. If the normalized Fermi energy is much less than 1, then it says that the Fermi energy is much below the conduction band. Then this integral simplifies and becomes an exponential, and that makes life easy. That's a non-degenerate semiconductor. In a non-degenerate semiconductor, this complicated Fermi-Dirac integral reduces to the familiar exponential. There's also a nice property related to the derivatives. So we are going to avoid the use of this throughout the remainder of the course. I want you to understand how to do the calculations and use Fermi functions, because you might encounter situations where you need to do that. These notes that I can refer to you really contain all you need to know about using Fermi-Dirac integrals in semiconductor problems. One thing I want to point out is that if you're reading papers or books, you have to be very careful. People sometimes define a Fermi-Dirac integral without this normalization factor out front. Usually when they do that, if they're being careful, they use a Roman F when they're defining it that way, whereas we're using a script F here. But people aren't always even careful about that. So you have to be very careful when reading books and papers that you understand which version of the Fermi-Dirac integral that they are talking about. The one that we have encountered is the Fermi-Dirac integral of order 1/2. J is equal to 1/2. And that Fermi-Dirac integral is defined this way. The quantity eta f is the normalized Fermi level. If I plot that function as a function of eta f, when eta f is much less than 0, the Fermi level is way below the conduction band and the semiconductor is non-degenerate. When eta f is above 0, the Fermi level is above the bottom of the conduction band and the semiconductor is degenerate. You can see for non-degenerate semiconductors, the Fermi function is equal to the exponential, and that simplifies matters greatly. The Fermi function is always equal to or less than the exponential for a given argument eta f. So in this non-degenerate assumption, when the Fermi level is way below the bottom of the conduction band, we have a very simple relation between the carrier density and the Fermi level. It's just an exponential relation. That's the one we're going to use throughout the bulk of this course. I'll remind you that a non-degenerate semiconductor is just one where the Fermi level stays within this shaded region and doesn't get too close to the bottom of the conduction band or too close to the top of the valence band. Okay, so we have succeeded in relating the electron density to the Fermi energy. In general, that relation involves Fermi-Dirac integrals that are a little bit complicated because we need to do them numerically. For a non-degenerate semiconductor, the relation becomes much simpler. A non-degenerate semiconductor, N-type semiconductor, has the Fermi level well below the bottom of the conduction band. The Fermi-Dirac integral reduces to an exponential, and the carrier density becomes the effective density of states times E to this quantity, this normalized Fermi energy. Now, we could go through the same calculation for holes. We would be interested in the probability that the state is empty. If we were to do that calculation, we would get answers that look much the same. We would get an effective density of states for the valence band times a Fermi-Dirac integral that depends on the normalized Fermi energy, which in this case is how far the Fermi energy is below the top of the valence band in units of kT. The effective density of states for the valence band would involve the effective mass for the valence band. In a non-degenerate p-type semiconductor, the Fermi-Dirac integral would reduce to an exponential, and we would have a simple exponential relation between the hole density, equilibrium hole density, and the Fermi level in a p-type semiconductor. Okay, so to summarize, we have discussed how one uses the Fermi function and the density of states to determine the concentration of electrons in the conduction band and holes in the valence band if we know the location of the Fermi energy. In general, these relations involve this complicated Fermi-Dirac integral of order 1/2 for parabolic bands. If the semiconductor is non-degenerate, the Fermi-Dirac integrals simplify to exponentials, and we are left with these two simple expressions that I'd like you to remember because we're going to use them over and over and over again. The electron density is equal to the effective density of states for the conduction band, which involves the conduction band of effective mass, times E to the Fermi level minus bottom of the conduction band over kT. So it's easy to remember the order of the Fermi level and the bottom of the conduction band because the higher the Fermi level is, the more probable the states in the conduction band are occupied. The density of holes in the valence band is the effective density of states for the valence band, which involves the valence band effective mass, and it depends on how far below the top of the valence band the Fermi level is. So these are expressions that are valid for non-degenerate semiconductors, and they're the expressions that we will be making use of for the remainder of the course. We will continue in the next lecture to discuss in a little more detail how the carrier concentrations vary as a function of the Fermi level.